Check 1, 2, 3. Check 1, 2, 3. Is it loud and clear? You can put in the chat now. In the chat, you can say whether it's loud and clear. Good evening, everybody. We'll start in another 10 minutes time. Voice check. Is it loud and clear? Anybody who is online can put in the chat. Is it loud and clear? Okay, great. Check one. Voice check one. Good evening, everybody. Welcome to another episode of Helpline. This is your helpline for the next 1 hour. We'll be discussing questions which you will find it sometimes difficult. We should also help you all to understand concepts and answer questions much more effectively and efficiently. Okay. Right. If you take page number 39, question number 40. Page 39, question number 40. Right, here we go. Page number 39, question number 40. Write down Bernoulli's equation for a fluid flow. Clearly identify all symbols. What quantity does each term in the equation represent? Right. Here we go. So you can write P plus half rho V squared plus rho GH. This is constant along a streamline. Constant along a streamline. So you can write it like this. Constant along a streamline. Now, there are many ways to explain this. You can say P is for pressure, rho is for density, V is for velocity at that instant, G acceleration due to gravity, or H is what height from the datum. Or you can directly give a direct definition. P is what? Work done by pressure per unit volume. P is work done by pressure per unit volume. What is half rho V squared? Kinetic energy per volume. Kinetic energy per volume. What is rho GH? Gravitational potential energy per volume. Okay. So like that also you can explain this particular term. So either way, whatever is comfortable, you can use it. What quantity does each term in the equation represent? Each term will represent what? Pressure. If you want, you can show it. Dimensions of P, ml minus 1, T minus 2. Half rho V squared. Here also separately you can work it out. Half is dimensionless. Rho density ml minus 3. V velocity LT minus 1 squared. Simplify this. ml minus 3. L squared T minus 2. Simplify it. ml minus 1 T minus 2. You can see its dimensions of pressure. Dimensions of pressure. Similarly, you can say rho GH. Rho GH. So what is rho? Rho density, ml minus 3. What is G? Acceleration LT minus 2. What is H? Height. Simplify this. ML minus 1 T minus 2. So each term will represent what? Pressure. Each term will represent pressure. Each term will represent pressure. Right. Then what are they asking you? During heavy winds, sometimes roofs of closed buildings are blown off. Use Bernoulli's equation to explain the phenomenon. Right. So we have done this. You all know how to do it also. But anyways, here you go. So here you have a roof. Here you have a roof. Now when heavy wind is blowing, you can draw a streamline. It gets very close over the roofs and then what moves away. Right? If you mark the pressure here as P1, velocity as V1, inside of course pressure is P2, we can say velocity is almost negligible. Zero. Now you can't apply Bernoulli's for two locations. It should be along the same streamline. Same streamline means along the streamline, somewhere far away, we say velocity is zero, so therefore same pressure will be there. Okay? Along a single streamline, same effect is there. The level difference is negligible. So A here, B here. Distance between A and B, we can say negligible. Negligible. Now we can write or apply Bernoulli's equation. We can take this as GP equals 0 line. So from here the height there, and from here the height there, both are what? Approximately the same. So if you apply, this is what you will get. P1 plus half density of air V1 squared, density of air G times H. Height here, pressure P2, half density of air, velocity is 0 squared, density of air GH, same height. Distance between A and B negligible, so same height. So you can see rho GH cancel off. P2 minus P1 is half density of air V1 square. Half density of air V1 square. So we can find, we can show here that P2 pressure is larger than P1 pressure. P2 pressure is larger than P1 pressure. So if you multiply it by the effective area, there will be a resultant force. So resultant lift force on the roof. Resultant lift force on the roof is going to be what? P2 minus P1 times effective area of the roof. Effective area of the roof. Okay, no? So pressure difference into area is 4. Simple, no? So pressure difference are pressure difference here and there. Pressure difference is given half density of air V1 square times effective area. There you go. So this is the lift force acting on the roof. So if you mark it very carefully, here there will be a resultant lift force acting in the upward direction. Remember, lift force is perpendicularly upwards. You can mark it like that. There you go. So from this you can find the lift force is half density of air V1 square times effective area. Effective area of the roof. Effective area of the roof. Okay, no? So remember, there will be a pressure difference. Higher velocity, low pressure. Low velocity, high pressure. So high pressure inside the hole. This will create a resultant pressure force in the upward direction. That resultant pressure force is called what? The lift force acting on the roof. Okay. Right. Then what are they asking? Here you go, the question. A narrow stream of gas blows out of a gas jet in the horizontal direction. In order to measure the speed of gas at the outlet of the jet, a student uses a U-tube, which is open at both ends and containing an oil. So we'll draw the picture. So here you go, U-tube is there. Here you go, there's a U-tube. And there is an oil as well. There you go. There is an oil as well. Right. What are they saying? In order to measure the speed of gas at the outlet of the jet, a student uses a U-tube which is open at both ends and contains oil. When the U-tube is held vertical to the outlet, so one of its ends is in the gas stream. So now there is a gas stream going on one end, not on the other. Gas stream goes on top of one end. So if the U-tube is like this, gas is going on top of one end. On the other end, there is nothing going. Okay. So to draw this 3D, I'll slant it and draw it. To draw it 3D, I'll slant and draw it. Here you go. Now here there is a stream of gas going. Stream of gas going very fast. Here pressure P1, velocity V1. Now tell me, higher velocity, low pressure. Low velocity, high pressure. High pressure here will push, this will go up. Okay, no? High velocity, low pressure. This side, low velocity, high pressure. This side, there will be a push. Push here means liquid will rise up. So here you go. Liquid rises. On the other side, liquid level is low. On the other side, liquid level is low. There you go. Now this will give us a level difference. This will give us a level difference. Now please be careful. Here you have pressure P1 acting. Here velocity is 0. There is pressure P2. P2 is acting here. Low velocity, high pressure, high velocity, low pressure. You have to apply Bernoulli along a single streamline. Remember, air is going over this, not on above that. So somewhere along the streamline at the same height, you have P2 and velocity 0. Same height from the ground. Same height from the ground. So you can say here, P1 and P2, or you can name these points A and B, points A and B, points A and B are in the same level. Are in the same level. So no change in the gravitational potential energy. If you want, we can take this as Gp equals 0 line. No problem solved. Now we apply Bernoulli's principle. Apply Bernoulli's equation. Apply Bernoulli's equation. Once you apply Bernoulli's equation, P1 plus half density of air V1 squared, no height, Gp equals 0 line. Pressure P2, no velocity. Simplify this carefully. What are they asking you? So here, simplify it slightly further. Half density of air V1 squared equals P2 minus P1. Equation number 1. All of you know the U-tube problem. Pressure here, same. Pressure at X equals pressure at Y. Pressure at X is P2, pressure at Y is P1 plus H density of oil into G. P2 minus P1, H density of oil into G, equation number 2. Now what can you say? Equation 1, equation 2 are equal. 1 and 2 are equal, you can substitute, no? Right? No? You are applying Bernoulli for the single streamline. Since you're applying Bernoulli for the single streamline, this pressure somewhere far away, same pressure, same velocity. Low velocity, high pressure. Low velocity, high pressure means you'll push on the liquid more, this will rise, that will go down. Now there is a pressure difference. I can't apply Bernoulli here and here. I must apply Bernoulli along a single streamline. Okay. Since I need to apply Bernoulli along a single streamline, here you go. We apply Bernoulli along a single streamline. Equation found. Once you find the equation, you can also find the pressure difference by equating the pressures in the U tube. Now substitute. Half density of air, V1 squared equal H density of oil into G. What are they asking you? Find the speed of the gas. So V1 squared, 2G H density of oil over density of air. And now carefully substitute. G is 10. Height difference is 2.4 centimeters. 2.4 centimeters convert to meters. Density of oil is given 800. Density of air is given as 1.2. Simplify this carefully. 1.2 times 1, 1.2 times 2. 1.2 times 1, 1.2 times 2. If you simplify it, V1 squared equals 2 times 2, 4. Simplify it carefully. 2 times 2, 4. 10 here. 10 to the power minus 1, you have 80 there. You have 80 there. Can you simplify this further? Yes. 16 times 5. Now you can take the square root velocity V1. Square root 4 is 2. Square root 16 is 4 root 5. 8 root 5 meters per second. 8 root 5 meters per second. Now remember, when you take, always at least keep it for 2 decimal places, because generally that's much more easier and accurate when you calculate. Easier and accurate when you calculate. So if you calculate this, root 5, 2.24, let's say. Root 5 is 2.24. So if you simplify this, 8 multiplied by 2.24, 32, 3, 16, 19, 17. 17.92 meters per second. Okay. 17.92 meters per second. There you go, the velocity. So you can see the work that we have done. Here you go, the YouTube problem. Now there's an airstream going over. There is no air going over this. So pressure there P2, velocity 0. Higher pressure there, liquid level will change. Along this single streamline somewhere far away, same pressure, same velocity, apply Bernoulli's equation. Once you applied Bernoulli's equation, we have equation number 1. Then we can say pressure at x equal pressure at y, equate the pressure. Once you equate the pressures, you can find the velocity of the stream of air. Once you find the velocity of the stream of the air, simplify it. Once you simplify it, here you go, 17.92 meters per second. 17.92 meters per second. 17.92 meters per second, that's the speed of air. Right, Roman 1 done. Roman 2, if the area of cross section of the gas stream is 10 to the power minus 4 meters squared, find the rate of mass flow. You know mass flow rate. Mass flow rate is A rho V. A rho V. Roman 2. Mass flow rate. Mass flow rate of air. So here you go. A V1 density of air. Area is 10 to the power minus 4. Velocity is 17.92 multiplied by density of air 1.2. Don't forget, you'll get the unit in kilograms per second. Kilograms per second. If you simplify this, you will obtain the relationship 17.92 multiplied by 1.2. That's going to be 2.15 10 to the power minus 3. 2.15 10 to the power minus 3 kilograms per second. 2.15 10 to the power minus 3 kilograms per second. Third one. What is the power of the gas state? When they say power, a lot of things will come to your head, but remember, work in terms of energy. What's the energy the gas stream has? It has a velocity. Velocity means kinetic energy, right? So power of the gas jet. Power of the gas jet that you can write kinetic energy over time. Kinetic energy over time is half mv squared over time. What is m over t? Mass flow rate. Do the substitution carefully. Half 2.15 10 to the power minus 3. Velocity of the air stream 17.92 squared. You will get the power in terms of what? You will get power in terms of what? So you can simplify this quickly. Here you go. Simplify this 17.92. Point 345. 0.345 watt. 0.345 watt. There you go. So interesting question. Once you find the gas stream, then you can find the mass flow rate. Once you find the mass flow rate, you can easily find the power of the gas jet. Power of the gas jet is given by the equation, or power means what? Work done over time, or energy over time. What does the gas jet have? Gas jet has what? Kinetic energy. Kinetic energy over time, you can find easily 0.345. 0.345. 0.345. Okay. Right. We move to the next question, question number 15. We move to the next question, question number 15. Here we go. Bernoulli's equation of fluid flow can be written as P plus half rho V squared plus rho GH is constant, where all symbols have their usual meaning. A Roman 1. State the conditions under which Bernoulli's equation is valid. So what are the conditions? Earlier question also there are. Non-viscous, incompressible, streamlined flow. Streamlined flow. Non-viscous, incompressible, streamlined flow. Right. State that the above equation is dimensionally correct. So because I have done this earlier, also I won't do it again. But I'll show it earlier. Earlier also, look at this. Earlier also I showed it. How did I show it? Each term I found the dimension. Each term I found the dimension. And those dimensions are equal to pressure. Since those dimensions are equal to pressure, this is what dimensionally correct. Okay, no? Each of these terms separately have dimensions of pressure. Because each of these terms have separate dimensions of pressure, the equation is dimensionally correct. Okay, right. I won't show that because I've done it. Part B. Part B. The insecticide sprayer shown in the figure has a pump of diameter 60 mm. So spray can, body spray, insecticide spray, all the principles are same. So here you go. So there you go, the tube is there. So here you have the piston cylinder arrangement. That's how pushing it that way, I guess. Here inside you have a vessel. Inside this vessel, of course, you have a liquid. Don't forget. Now what? Diameters are given. I hope you remember only up to the point where air is coming, you can apply Bernoulli. After this, you can't apply because it's what? Turbulent flow. What flow? Turbulent flow. Somebody tell me in the chat. Why do we call it turbulent flow? Somebody tell me in the chat. Why do we call this turbulent flow? Why do we call it turbulent flow? Somebody in the chat quickly tell me. Why do we call it turbulent flow? Someone quickly. Kamal, Ayman, Zainab, Anna, somebody quickly tell. Why do we say after liquid mixers with air, we can't apply? Very good, Hannah. Liquid getting mixed with air. Mixing means it's not streamlined. Very good. So here you go. Pressure is P1. Velocity is V1. Here pressure P2. Velocity is V2. Right. Read very carefully. An insecticide sprayer shown in the figure has a pump of diameter 60 mm. This pump is 60 mm. And this tube here is 2 mm. Insecticide level is 90 mm. Here it's 90 millimeters below. 90 millimeters. Assume that the pressure at A is same as the pressure at B. Pressure at A is same as the pressure at B means here also same pressure. Here also same pressure, pressure P1. Right. A Roman 1. Calculate the minimum speed with which piston P of the pump should be pushed. If the air jet in the tube Q is to contain insecticide. Right. Very good. So when I push this, I'm pushing it with a velocity V1, same velocity this particle has. Whatever velocity I push the piston, same velocity this air particle will have. Air will travel large area, low velocity, small area, high velocity. Small area, high velocity. High velocity means low pressure. P1 is larger than P2. Inside pressure is also same as pressure there. Inside pressure is large. When inside pressure is large, what happens? Liquid will rise. Liquid will rise and then start to mix. Mixing part we can't apply, but the rising part, here you go. Rising part is there. There you go. Right. So they want you to find the speed there. Right. Let's work. This is fairly a very good question. What we can do is we can say same level is your GP equals 0 line. Okay, let's work. Apply continuity equation. Let's apply continuity equation. Larger area A1 V1 equals A2 V2. So here you go, A1 V1 equals A2 V2. Pi diameter. d1 divided by 2 squared velocity v1, pi d2 divided by 2 radius squared v2. Simplify this, pi and pi cancel off. d1 squared over 4 v1, d2 squared over 4 v2. 4 cancel off. What is diameter d1? 60 millimeter. I'll do in millimeter. Millimeter squared will cancel off, no problem. 60 squared v1. The other one diameter is 2 squared. 2 squared v2. Simplify this. 60 squared. 3600 divided by 4 v1, that is equal to v2. Simplify it one more step. Therefore, we can say v2 is equal to 900 v1. v2 is equal to 900 v1. Right. Let's apply now. Apply Bernoulli's equation. Apply Bernoulli's equation. If you apply Bernoulli's equation, P1 plus half density of air V1 squared, P2 plus half density of air V2 squared. Our job is to find the velocity of V1. So we write V2 in terms of V1, P1 plus. We solve in symbols at the very end, substitute easy. P2 plus half density of air 900 V1 squared. 900 V1 squared. Carefully simplify. P1 minus P2 half density of air 900 squared V1 squared half density of air V1 squared. Common terms, take it out. P1 minus P2 half density of air V1 squared 900 squared minus 1. Now they are checking your basic common sense. 900 squared is how much? 900 squared. How much? If you take 1000 squared, 1000 times 1000, 1 million. 900 squared is going to be what? 8,100,000. So subtracting 1. So whether you subtract 1 or whatever, approximately it's equal to 900 squared. So 900 squared minus 1 is approximately 900 squared. You should realize this. Therefore, you can say P1 minus P2 is half density of air V1 squared 900 squared. There you go. We'll name this equation star if you want. So you can clearly see a very interesting connection. You can't randomly solve and go, but once you reach here, please don't go and subtract. It won't make much of a difference. It will complicate your calculation. 900 squared minus 1 approximately is 900. 900 squared minus 1 is approximately 900. So P1 minus P2 half density of air V1 squared 900 squared. 900 squared. Right. Now what? Now let's solve this further. We can also say like this. No? Liquid just rises, so P2 plus H rho G is equal to P1. P2 plus H rho G is equal to P1. P2 plus H density of insecticide into G equal P1. P1 minus P2 is height density of insecticide into G. I'll name this double star. That you can clearly see now, this relationship you can clearly see now. We have done so many applications. The moment you see this, you'll realize P2 plus H rho G equals pressure here. P2 plus H rho G equals pressure there. Quickly you can build the relationship. Now what can you say? Star equals double star. Star equals double star. Simplify it. H density of insecticide into G half density of air V1 squared 900 squared. Height is given as, now substitute, 90 millimeters, convert to meters. Density of insecticide is 1000, G is 10. Density of air is 2. V1 squared 900 squared. Minus 3 plus 3 cancel off. Simplify here. Simplify here, you have 900. 2 cancel off. 900 squared, V1 squared. 900 cancel off. V1 squared is equal to 1 over 900. From this you can simplify and say V1 equals square root 1 over 900. That is going to be 1 over 30. V1 is 0.033 meters per second. For 1 over 30, 0. For 10 we don't have, for 100 we have 3. For 100 again we have 3 reoccurring number. 0.033 meters per second. So you can see here, there's a nice progression in the question. There's a nice progression in the question. If I show it again from the beginning, here you go. What's happening is, the moment I push from this, air is going to quickly rush. When air quickly rushes, large area, small pressure. Sorry, large area, small velocity, higher pressure. Once it quickly goes here, high velocity, low pressure. High pressure to low pressure, air will quickly travel. Now the pressure inside the container is large because these two pressures they have said it's equal. It will push on this, the liquid will rise. It will push on this, the liquid will rise. So we applied equation of continuity. We have applied equation of continuity there and here. Got a relationship. And we have applied Bernoulli's equation along a single stream line. Once you reach here, guaranteed you must make this approximation. Otherwise, the calculation will be complicated. Once you make the approximation, simplify it further. Once you simplify it, you can find very simply the velocity V1. Very easily do the simplification. You can easily directly find the velocity V1. That's the velocity of the piston. Velocity of the piston. Then what are they asking you? If the net resistive force acting on the piston of the pump is 20. Now here you have piston cylinder arrangement. Here you have a piston cylinder arrangement. If you have a piston cylinder arrangement, they are telling you the net resistive force is 20 Newton. Determine the force that has to be applied on the piston. So they are asking you to find the external force. External force applied. Now the resistive force is going to be 20 Newton. Now all of you all know this is going with a constant velocity, right? 1 over 30 meters per second. Constant velocity means acceleration 0. So according to Newton's first law, applied force and resistive force both are what? Same. So you can actually apply F equal ma forward direction on the piston. If you apply on the piston, external force minus 20 Newton, mass into constant velocity, no acceleration. So external force is going to be how much? 20 Newton. External force is going to be 20 Newton. Simple. So there you go. It's a very simple, direct question. Simple, direct question. Simple, direct question. Very important as well. Simple, direct question. Right. Now you can take page 40, question number 16. Page 40, question number 16. Page 40, question number 16. Carefully look. So they have given you a hydraulic braking system. A hydraulic braking system. So here you go. This is point A. That's the axis. Here it's connected to a master cylinder, I think. master cylinder. Here you go. Master cylinder. Now what's happening is this will enter much more bigger piston area. That will enter much more bigger piston area. Call that the brake pad. Fluid will travel around. Fluid will travel around. Just draw it a bit carefully and correctly. There you go. Bigger piston cylinder with brake pad. Bigger piston cylinder with brake pad. There you go. There you go, fluid traverses. And here in the center, we have the wheel. Here in the center, we have the wheel. Axis of rotation is there. Axis of rotation is there. The wheel is rotating that way, let's say. So here you all have fluid. You have hydraulic brake fluid. Hydraulic brake fluid is there. Right. Hydraulic brake fluid is there. Right, now let's go to the question. Figure shows a hydraulic braking system which could be used to stop a rotating wheel. A force F is applied perpendicular to the brake. So we are applying a force perpendicular to the brake. Pedal rotates freely about a fixed axis A and perpendicular to the plane of the paper as shown. So when I press this, this will rotate about this axis. Pressure is applied on a master pump. The resulting pressure is transmitted to the brake fluid in identical pistons P2. So here identical pistons P2 are there. Here your master piston P1 is there. They are given you this distance 5 centimeter. And they are given you that distance how much? 20 centimeter. 20 centimeter. Cross-sectional area of the master piston 1 centimeter squared. Cross-sectional area of the secondary piston, here you go, 3 centimeters squared. There you go. So now let's try to understand what's happening. The moment you push this, above this point, equilibrium is achieved. So there is a anti-clockwise movement. To think carefully. Piston is pushing the liquid inside. Liquid is pushing the piston opposite direction. Here you go, the force. Liquid is pushing the piston, or piston is pushing the liquid inside. Liquid is pushing the piston in the opposite direction. Force divided by area is pressure. Force divided by area is pressure. Pressure in hydraulics will obey Pascal's principle. Pressure is equally transmitted everywhere. Pressure, fully enclosed fluid, equally transmitted everywhere. Even here you have pressure P. Pressure multiplied by area will give you a force. Brake pads will come closer. These brake pads will come closer and touch the rotating wheel. So if I draw the rotating wheel here, brake pads will come and touch. On this side, it will touch here. On the other side also it's there. So from both sides, you have what? The brake pad being touched. From both sides. From both sides, you are applying frictional force. Frictional torque will slow it down. Okay, no? Frictional torque will slow it down. Right. Okay, no? Idea you got. So I apply the brakes here. Piston is pushing the fluid inside. Fluid is pushing the piston in the opposite direction. Then what happens is, about this you can take moments, you can find the force. Force divided by area is the pressure. Pressure is equally transmitted everywhere according to Pascal's principle. Pressure acting on this area will push on the piston touch. So if the wheel was rotating in that direction, there will be a friction force opposite. Friction force opposite. The force given by the piston is the normal reaction. That's only pushing on the wheel inwards this way. That's the normal reaction. On the other side also, don't forget, on the other side also there's another brake pad. Here brake pad is there. On the other side also brake pad. Blind side also there's a brake pad. From both you will have a friction force acting. These from behind that. Both you will have a friction force acting. That will cause frictional torque. Frictional torque will slow down the speed. I hope you understood this concept. Okay. So before you solve the problem, try to understand what's happening in the problem. Once you understand what's happening in the problem, calculation part, of course, it will be much more easier, much more simpler. Roman 1. When a certain force is applied to the master piston, it moves a distance 0.6 centimeter to the right. So it moves 0.6. How far does a single brake pad move? So when you move this, that liquid is moving forward. That volume is equally divided. Part of that total volume goes here. The other half goes there. So you can do this question very easily. Roman 1. Displaced volume in master piston. Displaced volume in volume by master piston. Cross-sectional area into the length. Area there is going to be 1 centimeter squared into 0.6. 0.6 centimeter cubed. Displaced volume by master piston. Volume added to secondary piston. To one secondary piston. The volume added is also going to be the same, 0.6. Area is 3 times x. X is equal to 0.2 centimeter. Sorry, exactly half. No? Half of this. Huh? Sorry. Half of this, 0.3. Total volume is divided, so half of this will go 0.3. 3 times x. Simplified, 0.1 centimeter. So one brake pad will move 0.1 centimeter. One brake pad will move 0.1 centimeter. Right. Next one, Roman 2. Next one, Roman 2. If F is 10 Newton, so you are applying F 10 Newton, what is the applied force on the piston P1 on the master pump? The applied force F1. So Roman 2 part A, clockwise moments about A equal anti-clockwise moments about A. Clockwise moment is F1 times 5. Anti-clockwise moment is 10 times 20 centimeters. Centimeter means F1 is equal to 40 Newton. That's the force on the master piston. Calculate the pressure exerted on the master piston. You can find it. Pressure is equal to force divided by area. Yes. Pressure here P1 is equal to force. Piston is pushing the liquid inside, liquid is pushing the piston outside. So F1 is acting on the liquid as well. F1 over area is pressure. F1 over area is pressure. F1 40, 1 centimeter squared 10 to the power minus 4. Simplify it. 40 10 to the power minus 4 4 10 to the power minus 3 Pascal. 4 10 to the power minus 3 Pascal. So centimeter cancel off. So here you will get your answer in Newton. Newton divided by area. Area is given as 1 centimeter square. Centi minus 2 to the power 2 minus 4. From there you get 4 10 to the power minus 3. Sorry. If I take on top plus. If I take on top plus. If I take this on top plus. 4 10 to the power 5 Pascal. Okay, no problem solved. Right. Then what? Calculate the force exerted on the brake pad. Now, according to Pascal's principle, pressure is equally transmitted to every part of the fluid. So this pressure which you calculated here, this pressure is transmitted here as well. This pressure is transmitted there as well. So now you can answer this question. They're asking you force exerted on the brake pad. Force on the brake pad. Force on the brake pad is pressure multiplied by area of the brake pad. Pressure is equal to 4 10 to the power 5, same pressure. Area 3 centimeters squared, there you go. Simplified, force is 120 Newton. Force on one brake pad is 120 Newton. Part D. Part D. I have shown you here now. I told, if this is the brake pad, you are pushing on this. That is your normal reaction. I am pushing with 120. The brake pad is pushing my hand with 120. So here 120 normal reaction. They are asking you, calculate the frictional force. Frictional force is mu k times normal reaction. Normal reaction is this applied force by the brake pad. Coefficient of friction 0.5. Normal reaction 120. Friction force is 60 Newton. Friction force is 60 Newton. There you go. So the wheel is rotating. You are applying brake. The brake pad is applying 120. Let's say these are brake pad. Hand is pushing on the wheel with 120. Wheel is pushing on the hand with 120. So normal reaction is 120. Right. So there you go. So again from the beginning I'll explain. So they are telling you master piston will move 0.6 centimeter. So what's the volume displaced? Area into distance is going to be volume 0.6 cubic centimeter. That volume will equally divide among these two. So on one piston, half of this 0.3. 0.3, then how far will the piston travel? 3 times x, 0.1 centimeter. Now they are telling I'm applying brake. I'm applying brake here. When you apply brake, about this, it will go anti-clockwise. They are clockwise. Clockwise movements should balance anti-clockwise movement. How will there be a force here? Piston will push the liquid in that direction. Liquid will push the piston in the opposite direction. So here you can find the force. Force divided by area is pressure. Pressure is equally transmitted here and here. That's the connection. So here we can find the pressure 4 10 to the power 5. Same pressure will be there near the brake pad. Same pressure will be there near the brake pad. Pressure into area will give you force on one brake pad, 120. Now the wheel is rotating, brake pads are touching. Normal reaction 120 means friction force is 60 Newton. Friction force is 60 Newton. Right. Now look at Roman 3. Look at Roman 3. Roman 3, what are they asking me? Roman 3, what are they asking me? Before applying the brakes, wheels were rotating at 600 revolutions per minute. So before applying the brake, omega was 600 revolutions per minute. Okay. If the distance from the rotating axis where friction is acting is 5 centimeter, so here you have your brake pad. Here you have your brake pad. The distance from here to here is 5 centimeter. Don't forget friction will act in both directions. Friction here, opposite side also there is friction. Both sides there is friction. How long does it take for the wheel to stop? Right. Superb question. Superb question. How long will it take for the wheel to stop? Observe. First, torque equals I alpha. We must find the angular deceleration. Tell me now, this is rotating this way. The frictional torque is in the opposite direction. So there is resistive torque. Resistive torque is minus. How do you find the torque? Friction multiplied by distance 5 centimeter. That is torque times 2. By both sides there is brake pad. Moment of inertia is given 0.1 times alpha. So don't be in a hurry. Why is the wheel slowing down? The wheel is slowing down because of friction. What friction? Friction from the brake pad. The rotational motion. So what is it creating? Frictional torque. It's creating frictional torque. So what is your friction? 60 times 5. 10 to the power minus 2 times 2. 0.1 alpha. 300. Sorry, 60 times 5, 300. 300 times 2, 600. Minus 6.1 alpha. Now what? Jump a decimal. Alpha is minus 60 radians per second square. Radians per second square. Once you know the angular deceleration, initial omega naught 2 pi n over 60 you can substitute. Pi is 3 given. Number of revolutions is 600 divided by 60. So here 10 times 6, 60 radians per second. Omega naught. Time taken for it to stop. Omega equal omega naught plus alpha t. Finally 0. 60. Alpha is minus 60 times t. 60 times t is equal to 60. T is equal to 1 second. In 1 second, the wheel will stop. 1 second. How many revolutions does it make before it comes to rest? How many revolutions means rotation? Theta equal omega naught t plus half alpha t square. Initially 60 time 1 second. Alpha is minus 60 t squared 1 second. 60 minus 30, 30 radian. Theta. Number of rotations. How do you find the number of rotations? Number of rotations. Theta divided by 2 pi. 30. 2 times pi is 3. 10. 5. 5 rotations before it comes to rest. 5 rotations before it comes to rest. You can see it's a very simple, easy problem if you understand the mechanics behind it. Understand the mechanics behind it. I'll go back again. First part, of course, you all know. First part we explained. Now we'll touch it from here back again. So friction will act from both sides. Piston is going to push on the brake pad with 120. So on the brake pad, the normal reaction is 120. On the brake pad, normal reaction 120. From there, we can find the friction acting on one side. So friction on one side, 60. So wheel is rotating this way. I'm creating frictional torque in the opposite direction. Frictional torque in the opposite direction. Friction into distance. Both sides there, so multiplied by 2. From there, we can find alpha, minus 60 radians per second. Substitute here, we can find the time. Once you find the time, they are asking number of rotations taking place. Find theta, total number of rotations, divided by 2 pi is number of rotations. That's going to be what? 5 rotations taking place. You can see fluid motion connected to what? Rotational. Fluid motion connected to rotational. Okay. So you can see today we solved 3 super essay questions. Keep on solving. We will meet again next week for another episode of Helpline. I hope this section would, this effort that we are putting is helping you all. And you all should do the questions as well. Once you do the question, then it's easy for you all to check where you went wrong, where was your place, where you were thinking wrong, and your thinking will greatly improve. Is it clear? Okay then. Until next time, keep working smart, keep working efficient. Good night.